Hello student, here we start off with the topic of complex numbers. As we see the introduction to these complex numbers, let us first understand the motivation behind why do we need the complex numbers in first place. Just to set the stage for this, let us consider a simple equation, that is, say x plus 2 is equal to 5. Now if we give this equation to solve to some child who knows only the natural numbers, then we will definitely get an answer that x is equal to 3, because it's a number which satisfies this particular equation. But if we give the same child a slightly different equation to solve, now here what happens is, we know that this equation is not solvable in natural numbers, because there is no natural number x which satisfies this equation. So that means we have to broaden or expand our understanding of numbers, and now we need to include the integer numbers also if we want to solve this type of equation. And here we know that x is equal to -3 will definitely solve this equation. But as we move ahead, we see that even the integers are not sufficient to solve the equations of this particular type. Say 2x is equal to 1, because here we know that x is equal to 1 by 2, which is not an integer. So that is where we bring in the rational numbers, that is the numbers of the form p by q, where p and q are integers which are the co-prime to each other, and q is a non-zero integer. Moving ahead with the same logic, we will find that there are some equations which are not solvable in even rational numbers. Say for example, if we have something like x square is equal to 2, which gives us x is equal to root 2, and we know that root 2 is not a rational number, it's an irrational number. So therefore we are now at a juncture where we have covered the rational numbers as well as irrational numbers. So together they make up what is called as the set of real numbers. Now let's see one step ahead, and we will come to know that even real numbers are not sufficient to solve certain equations. Say here we have an equation as x square plus 1 is equal to 0. Now if we consider this, it gives us x square is equal to -1. And so far, if we know only the real numbers, here we see that square of real number is -1, which is not possible if x is a real number. So that is where we are now in need of defining an additional set of numbers so that we can solve such types of equations. So that is where we bring in the imaginary numbers, and along with real and imaginary we get what is called as a set of complex numbers. So now let us see the formal definition of complex numbers. A complex number, typically it's denoted by letter Z. It's a number of the form a plus b into I, where a and b are real numbers and I is defined as the square root of -1. This is what is called as the imaginary unit, as we have seen in the previous example where x square was equal to -1 and we were not able to solve it in real numbers. So this is where we specifically define the number I as the square root of -1. So any number of the form a plus bi, where a and b are real and I is equal to root of -1, is called a complex number. Now if we see this a, which is real part, we call it as real part of z, whereas b is called as the imaginary part of the complex number z. Note that it is customary to call only b as the imaginary part and not bi as the imaginary part. So a and b, although they are themselves real, we call real and imaginary parts of z as a and b. So writing that in the notation we have Re into bracket z, which stands for real part of z, which is nothing but a in the above example, and Im into bracket z, which stands for the imaginary part of z, which is b. So now just to take some example, let's consider the number 3 plus 2i. So here the real part is nothing but 3 and the imaginary part is 2. Now it may happen that either of a and b could be 0. So let's consider the number something like say 5. Now here we see that there is no term containing I. So therefore we say that this number is purely real because it contains only the real part in it. On the other hand, if we consider a number something like this, say 2i, now here we see that there is no real part in it, there is no a component in that. So such number which contains only the imaginary part is called as purely imaginary number. Now let's move ahead. Now here we see the equality of two complex numbers. That is, if we have one complex number a1 plus ib1 equal to another complex number say a2 plus ib2, then it implies that the two real parts must be same and the two imaginary parts must also be same. So therefore we have a1 equal to a2 and b1 equal to b2. Now we have to note one important thing about the complex numbers is that the order relation between two complex numbers is meaningless, that is, it's not defined. So in other words, it means that it is invalid to say whether z1 is greater than z2 or z1 is less than z2. So basically we cannot arrange them in that particular order. We can only have their equality if at all it is possible, but not the order relation between the complex numbers. Now let us see the various integral powers of I. That is, what do we get when we raise this number I to different integer powers. So for that, let us start off with the simplest, the known power I raised to 1 is nothing but I, as we know. Now if we consider I square, that will come as minus 1 because the very definition of I was nothing but square root of minus 1. Now if you consider I cube, which is nothing but I square into I, and since I square is equal to minus 1, therefore I cube turns out to be minus I. Then we have I raised to 4, the fourth power. Now this you can visualize as I square into I square, which is nothing but minus 1 into minus 1, which makes it plus 1. Now if we consider the next power, that is I raised to 5, here we will see that we can take out the power I raised to 4 from it, so that only I remains, and therefore since I raised to 4 we have seen that it is equal to 1, therefore I raised to 5 turns out to be ultimately I. So moving ahead, I raised to 6 can also be similarly written as I raised to 4 into I square. So we get back I square, which is nothing but minus 1. So hence I raised to 6 is minus 1. Then I raised to 7 is nothing but I raised to 4 into I cube. So now here we are getting I cube as the value, which is nothing but minus I. And lastly in this example, I raised to 8 is nothing but I raised to 4 into I raised to 4. Here we are at I raised to 4. So therefore it's 1 into 1, which is 1. So if we observe the pattern, that is, here we have I, here we have minus 1, then minus I and 1. So the same pattern now continues for all the subsequent powers. So that is where we can now generalize and write down the different powers of I as follows. Now for that, let us start off with these powers, which are the multiples of 4. So we can write that I raised to 4n is equal to 1. Now here we have n as a natural number. So when n is 1, the smallest value of 4 into n will be 4. So that makes it I raised to 4 as 1. So therefore 1 power less, that is 4n minus 1, will be nothing but the powers I cube as well as power I raised to 7 and so on. So that will be equal to minus I. Then going one step back, we have I raised to 4n minus 2 is nothing but minus 1. That is where we have I square, I raised to 6, I raised to 10 and so on. And lastly we have I raised to 4n minus 3 to be equal to I, which are nothing but the powers of I raised to 1, I raised to 5 or I raised to 9 and so on. So this is the relationship between various powers and the values of those powers. So this is where we can remember the integral powers of I.